You good? You happy over here?
Oh, I'm never happy.
Content? Okay. All right, everybody. Hope you had a good weekend. I apologize for not having your mini exams done yet. I'm halfway through them, and I should be done with them later today. So I apologize. We got a lot of stuff going on right now in the math department in terms of administrative things. So I've been sidetracked with that sort of stuff. All right. So we are going to move into the next section. Who was asking about the center of mass? Is that you? Okay. So I wanted to tell you, because I can explain it, but I think the book does a tremendous job of explaining it. 7.6 in the book, they explain the rationale for finding center of mass and why it is that computation. But they do it in terms of kind of an easier, it's back in chapter 7 because it's applications of definite integrals. And then it can be extended into higher dimensions. So I don't think I could draw it any better, or explain it any better. So go ahead and take a look at that. And if you have questions, we can talk about it. Okay? All right. 12.5. 12.5, triple integrals. So what we've been doing, right? What we've been doing with double integrals is that our domain, right, lived in two-dimensional space, and then the function, right, would create that third dimension. Now what we're doing is we're saying, what if our domain is three-dimensional, right? What if we have a three-dimensional domain? And that would be where we get this idea of triple integral. So reminding us again of how this all came about, in Cal 2, we did a regular integral, and we did it over some interval a to b. And so on a number line, this line segment was our domain, right? And then now we've looked at double integrals over some domain D, and in two-dimensional space, this is our domain, right? And now we're going to be looking at triple integrals, right, over some region, we're going to call it E. And as you might suspect, the domain then would live in three-dimensional space. So it's going to be some sort of solid three-dimensional shape, whatever it might be, but it's three-dimensional, right? This is our E. So linear, right? One-dimensional, two-dimensional, three-dimensional. So when we did double integrals, what was the first type of region we started with double integrals? What was the first type? The rectangle, right? Rectangle. Our x's were between constants, y's were between constants, and then we expanded to type 1, type 2, and then we did polar, right? So we're going to do something similar for triple integrals. The most simple, solid shape that we can have as a domain would be a box, right? Or a rectangular box. And so that's where we start. That's the first definition here. So the triple integral over the region E, all right, where the shadow cast on the xy plane is a rectangle is given by these sets of inequalities. So E is the box where our x's are between two constants, A and B, our y's are between two constants, C and D, and our z's, our up and down, is stuck between two constants, R and S. So here's the picture. That's looking at this from the top. Notice our x's are between two constants. Our y's are between two constants, right? And our z's should also be between two constants. So when I flip this and rotate this, we can see that our z's, right, our z values are between two constants. So that is our domain, okay? So we're taking the points within this box, we're plugging it into some function, and that's going to spit out some number. And then what we want to do is add all those up. Okay, so that's what the triple integral is going to do, is add up all the values of some function where that is the restricted domain. So here's the notation for it. If we're using a box, we do triple integral over E. We have to have some function we're integrating, so some function of x, y, and z, because now we have 3 inputs. And then notice dv, right? dv. I want to remind you again, or talk about that because it's important. Our original integral from Cal 2, a to b, right? What was the d here? D what? No, in Cal 2. We started with dx, right? And the most you could do is change that to dy. And all that is this little infinitesimal width, right? dx. When we did double integrals over some domain, it's dA here, right? Where A is some infinitesimal little patch within here, right? That's our little dA. And now we're doing a triple integral over E, and we've got this solid shape, right? And what we're going to do is take this little infinitesimal box, in there, and we're going to call it dV for a little infinitesimal volume, infinitesimal area, infinitesimal length, right? So this dV, what it is, it's dz, dy, dx. So it's like, length times width times height, which gives us the little volume. Oh, sorry. Okay. Now, look at the order of integration. You've got your function. The first integral, right, the inner integral, is with respect to z, so these are the limits on z. And then the next integral out is with respect to y, so these are your limits on y. And then your last integral, the outer integral, is dx, so these are your limits on x. What do y'all think? Can we switch it? Can we switch the order? As long as it's a box, right? If it's a box, we can switch the order, just like before. Let's do this example. So we want to evaluate this triple integral triple integral over E of x squared yz with respect to volume on 0, 2 cross 1, 2 cross O2, or sorry, O1, which is a box with these are your restrictions on x, these are restrictions on y, and these are your restrictions on z. So we should just be able to set this integral up. There's no picture. I don't need any picture, right? Do y'all want to draw the picture? We can. Do y'all want to draw E or not?
It's a box.
It's a box, right? Okay, so I think we can just go straight to it. Triple integral, order doesn't matter, so I'm going to do the x's on the outside, so 0 to 2. And then the y's next, 1 to 2, and then the z 0 to 1, and then I'm integrating x squared yz. And now this has to be in the right order, dz, dy, dx. Let's go ahead and grind this out. This first example, we had a whole weekend, right? Let's just grind this. So I'm going to start with the inner integral. So I'm going to leave the 2 outer integrals alone, 0 to 2, 1 to 2. And now I take the antiderivative of this with respect to what variable? Z. So I treat x and y like constants, so just ignore that. The antiderivative of z would be 1/2 z squared. And so this will just become 1/2 x squared y, z squared. Right? That's the antiderivative with respect to z. And I'm going to evaluate that from 0 to 1, right? And I'm going to put here z equals 0 to z equals 1. And I need to figure out what that is, and then I still have to do dy dx. The middle and then the outer integral. All right, it's real nice to plug in 1 and 0, right? Because when you plug in 1, this just becomes 1/2 x squared y, and when you plug in 0, everything goes away. So we should just have integral 0 to 2, integral 1 to 2, 1/2 x squared y dy dx. Any questions? I'm doing that in my head. I'm just plugging 1 in here, getting the answer, that's that, and then plugging 0 in kills everything. Good? All right, let's go. We're back to double integrals now, right? This is, I mean, we've done double integrals before, so same procedure. Take the antiderivative of this one with respect to y, which gives me another 1/2 y squared, or I get another 1/2 to come out here, so I'm going to have a 1/4 x squared y squared, evaluating that from y equals 1 to y equals 2. Man, I wish that were 0 down there. Dx. And when I replace this y here with 2, I get a 4, right? When I replace the y with 1, I get a 1. So turns out to be, what is it?
X squared minus 1/4 x squared.
X squared minus 1/4 x squared, which would be 3/4 x squared? Dx. And now we're back to Cal 2, right? And that's just a simple integral. So this is just going to be, this turns out to be what, 1/4 x cubed? Evaluate from x equals 0 to 2. And you just get 2. 8, 1/4 of 8 is 2, and then 0 in there kills it off. So you just get 2, right? All right, that's the mechanics of doing a triple integral over a box. Pretty straightforward, right? There's really just one more layer of integration to do in the middle, but other than that, it's what we've been doing.
So what is this answer mean?
Well, it depends on what the function represents. So the thing in here, right, this is the thing we're integrating. If we go back to last class and think about if this were the density function, okay, the density function showing you, it's basically giving you the density at every point in that solid, then this number would be the mass of the solid. It would be your total mass. Yes?
Is this going to be the same as double integrals where we can switch which ones we go first?
Yeah. As long as it's a box, you can switch it. You can't switch it if it's not a box, which is about to be what we're going to move into this, all right? So if you recall again from when we were doing double integrals, right? When we did double integrals, we started with a rectangle, right? And then we moved to type 1. Remember what type 1 was? X is between two constants. Y is between two functions of x. That's type 1. Type 2 was your y was between two constants, and your x was between two functions of y, right? Rectangle, type 1, type 2. That's for double integrals. So what do you think is coming now? Same sort of thing, right? But we have 3 variables, right? Which is going to be a little bit weird because there's going to be a lot of different sort of scenarios we could see. So here is our first non-box region, okay? This is our first region that's not a box. So this is a triple integral over some region E where whatever this solid is, if you were to take a light and shine it straight down, the shadow of that region on the ground is a type 1 region from double integrals. So let me see here. Take a look at this. We're looking at the solid from the top, okay? Like if we're above the solid, we're looking straight down. We can kind of see that our x's look like they're between two constants, right? And our y's look like they're between two functions of x. Y'all see that? That's like a type 1 from double integrals, right? The z is not between two constants though. So let me just pop this out of two-dimensional space. And you can see here that, see how the shadow of this object on the ground, the shadow of it on the ground is a type 1 region from double integrals, right? Type 1. And then the surface, look at this solid, has as a bottom surface u1 of xy, and then the top surface we're calling u2 of xy. So your z's are between two functions of x and y. Your y's are between two functions of x. And your x's are between two constants. Does that all translate okay on that image there? Okay. So I'll scroll back up. Here, our x is between two constants. Our y is between two functions of x. And then our z, right, our up and down, is stuck between two surfaces. So when you have this, here's what the triple integral looks like. Now order absolutely matters, right? Your outer integral, so it's the same notation, triple integral over the solid E of the function, the scalar function f of x, y, z, with respect to volume. Our outer integral is with respect to x, and those are our restrictions, our constant restrictions, right? Our next integral in is with respect to y, and those are our two functions of x. And then our inner integral is with respect to z, and these are our two surfaces, which are our restrictions on z. Have to go in that order, can't change anything. Yes?
Can the G and the U, the Y and the Z be swapped their order?
The y and the z,
Yeah, the two, yes.
these two, no.
No, they can't?
No. Mm-mm.
What?
Because this depends on this,
Okay.
not the other way around.
So if it was G of X, Y, and U of X.
Yes, yes,
then the other
yes, you could. But then you wouldn't call it g, you would call it u, because u is always the function of x and y. Like u1 and u2 are our functions of x and y, and the g is always the function of x.
Okay.
All right, understand? Let's do one. Evaluate the triple integral over E. Look at our function, very simple function, y, right? We're integrating y. With respect to volume. Now, what's the E? What's the solid we're integrating over? Well, these planes, right there, all of those planes. So x equals 0. What's x equals 0? That's the what plane? Y, Z. Let's see if I can get this right. This is, I never get this right the first time. I guess, yeah, let me do it this way. This is like a Rubik's Cube for me, I swear. What am I doing wrong?
I think you had it right before.
No, right rule. What's that? I painted them so I wouldn't screw them up, but, okay, so we want R, right hand rule, right? Red, green. I need this the other way. There we go. Jesus. It's a freaking puzzle. There we go. Right, x equals 0 is, this is x, right? Y, that's z. So x is 0 is the yz plane. Okay, y equals 0 is the xz plane. Z equals 0 is the ground, right? So we've got all the coordinate planes, and then this plane, which is just some plane with some tilt to it, right? So we're trying to figure out where this plane hits here. So we should have some sort of like shape over here, like from here, like it hits somewhere here, somewhere here, somewhere here. So we have this like triangular region that's at a tilt. Kind of see it or no? One of these days that's going to be useful. Hasn't happened yet though. All right, let me draw a picture. When I draw three-dimensional space, I do it different ways because I know in like a physics class, you might have someone who draws three-dimensional space one way, and then you take a math class, they draw it a different way. So I try and mix it up. Here's one way to represent three-dimensional space. All right, I'm going to actually draw this one first. So to do that, I'm going to figure out where that plane hits the different axes. So I'm going to let y and z be 0. If y and z are 0, what's x? 2? Okay, now let's let x and z be 0. So y is 2, right? And if I let x and y be 0, you get z is 4, right? So that's up here. So here, you can imagine a plane that goes through those 3 points, right? But then it hits the different coordinate axes, and so you should get some shape like this. It's that solid. Now, of course, my computer does a better job than I did. There it is right there. Okay. That's what we're integrating over. So I need to see, can I look at this as having my x's bounded between two numbers, my y's bounded between two functions of x, and my z's bounded between two surfaces? So let's start with, well, how about I draw this in two-dimensional space? Like, let's draw this when z is 0, then we're looking at this footprint down here. It would look like this over here. And this is 2, and that's 2, right? Looking at this region in two-dimensional space, this right here would be a type 1 region from double integrals, right? Here my x's are between 0 and 2. And my y's are between two functions of x. So I need to determine what those two functions of x are, right? Here's my y trapped between those two the whole time. And the bottom one is just 0, right? That's just the y equals 0. And then I need this line. I need the equation of that line, which has a slope of -1, right? And it has a y-intercept of 2. So negative x, almost, a little more, plus 2. You have to move that line up, right? You have to move that line up. You understand that? So my x's are between two constants, my y's are between two functions of x, and then now the z. It's hard to draw it on this, but the z is like, that's the top surface, which is the top of that thing, right? Like that's the top. And then the bottom of it, like, well, can you tell me what the equation of that is, or what that is as a function? This is our u2 of xy.
Z equals 4 minus 2y.
Yeah, you have to take this and solve for z, right? So just 4 minus 2x minus 2y, right? That would be the top of the solid. And then what about the bottom of the solid? What is that? Yeah, u1 of xy would be just 0, which is the ground, right? Z equals 0. So my z is bounded between 0 and 4 minus 2x minus 2y. There we go. Any questions on how I developed that or where I got any of that from? All right, we set up the triple integral now. I have to say it's not a bad picture. If I might critique myself on that. All right, triple integral starting with 0 to 2. Then 0 to negative x plus 2. And then 0 to 4 minus 2x minus 2y. What is the integral? What's the integrand? What's the thing we're integrating here? Y, right? Y, and now with respect to z, then y, then x, because I have to follow the order of this, right? Backwards, I guess. Go with z, then y, then x. I think we should grind this one out, at least until a point where we're like, okay, I think we're okay from here. So first I integrate with respect to z. So leave the two outer integrals alone. All right, the antiderivative of y with respect to z is yz. And we're evaluating that from what to what? Z equals 0 to z equals that function of x and y, right? 4 minus 2x minus 2y. And then dy dx. So we're going to replace z with all of that. and then replace z with 0. Well, the 0 is nice, right? The 0 is a good thing. Zero to 2, 0 to negative x plus 2. All right, what do we get here? I know when I plug in the 0, it's gone. So when I plug this in right here, everything gets hit with a y, right? So it becomes 4y minus 2xy minus 2y squared. dy dx. And now we're back to double integrals, aren't we? I'll go one more step, maybe two. So now I'm going to do the inner integral there. So antiderivative of this with respect to y. 2y squared minus xy squared minus 2/3 y cubed. Ugh. When y is equal to 0 to y equals negative x plus 2. Whatever that is, dx. So I'm integrating each of these with respect to y, right? Y'all good? Yeah. We have to replace all of our y's with this, and then all of our y's with 0. Well, y's with 0 is going to kill everything. So this, I think, is going to be my last step. This is now equal to the integral from 0 to 2 of, replace every y with that. So 2, and then negative x plus 2, that quantity squared, minus x times negative x plus 2, that quantity squared, minus 2/3 times negative x plus 2, that quantity cubed, whatever that is, dx. And as bad as that looks, we could just like expand that out, like FOIL that out, distribute a 2, FOIL that out, distribute an x, expand it, right? And then you'd have just this big polynomial. You could also do a basic u sub, replace x, negative x plus 2 with u and do a u sub. But I think at this point it's just a Cal 1 problem. I'm sorry, Cal 2 problem, right? May I stop? Yeah. Let me see if I actually got the answer on this one. I did not. Okay. Questions? Dot, dot, dot. Dot, dot, dot. We're all right? Well, that was an example where our shadow on the ground was a type 1 region from double integrals, right? What do you think's next? The shadow on the ground's a type 2. So this is what this one looks like. So looking at the solid from the top, why is my viewpoint, when I go top, oh, there we go. I just need to hit it. See, everything was skewed out. There, that's from the top. That's looking down on our solid. And you can see that our y's are between two constants, and our x's are between two functions of y. Right, so that's a type 2. And then the z values are, again, stuck between two surfaces. Where are they? Well, I'm not showing the z labels. There we go. So you can see our z values are, again, stuck between two functions of x and y. Okay? What's going to change? Yeah, it's just going to be y's on the outside, constant, then with respect to x with our two functions of y, and then our restriction on z. Very similar, right? Let's at least set this one up. I don't think I'm going to do any actual integration. I think just setting it up is all I'm going to do here. Evaluate the triple integral over E of xz dv, where E is the solid tetrahedron with these vertices. This has actually come up in your mini exams where I give you points and then you have to find a plane. But let me draw it again. So we've got x, y, z. 0, 0 is this point right here. 0, 0, 0, sorry. And then 0, 1, 0 means 0 on the x-axis, 1 on the y-axis, but don't go anywhere on z. And then 1, 1, 0 means out 1 on the x-axis, and then out 1 on the y-axis, which is going to put you about right here on the ground still. This is 1, 1, 0. This one was 0, 1, 0. And then I have one more point, 0, 1, 1, which means don't go anywhere on x, go out 1 on y, and then go up 1 z. So that's 0, 1, 1. It's the solid tetrahedron with those vertices. So it's going to look like this. Let's connect these two together. Then those, and then that, and then that. Do y'all see that solid? Again, my computer probably has a better picture of it for us. There it is. Whoa, whoa, oh shit. Now I'm confused. There we go. All right. So the shadow of that on the ground, right? Let's draw that next. Let's draw this thing. And the shadow of that on the ground is actually where this thing touches, right? It touches the ground there. So let's draw that. Make sure you get your axes in the correct position here. You have x, you have y. So the points I have here are at the origin, and then out 1, up 1, a point there, and then just up 1 like that. This is our region. Now that region, is it type 1 or type 2 from double integrals? It could be either one though, couldn't it? Couldn't this be either one? It could be a type 1 or a type 2. If you said type 1, x is between 0 and 1, and your y's are between those two, right? Or you could say y is between 0 and 1, and your x's are between those two. We have the freedom here to choose. It could be either type 1 or type 2, up to us. Let's do type 2 because that's what the previous note was about. So I'm going to choose to look at this as a type 2, which means I'm going like this. Ooh, that's a good marker. My y's are between two constants, 0 and 1, right? 0 and 1. And then my x's are between, let's say, over here is 0. And then what is this line right here? Y equals x, but we need to solve it for x, right? Because it's going to be a function of y. So this should be y, right? So remember, this right here is x equals y. We solve it for x, and then that's our function of y.